Alright, some notes on, before we get into our examples, some things that we need to know about. Number 1, slope angle. Slope angle. As you do your problems, you may come across that term. The slope angle is the angle opposite the rise By the way, I'm only going to use half of my page because I'm going to do another definition over here. Okay? Slope angle. The angle that is opposite the rise and adjacent to the run. So, if we drew a little right angle triangle here, a little diagram to help us understand this. Right here is our slope angle. Okay? Slope angle. And we said it is opposite the rise. So over here we have our rise. And adjacent to the run. And right here we have a run. And this is all happening inside a right triangle. Okay? Rise and run never move. And the angle in question, the slope angle, always is opposite the rise and adjacent the run. Adjacent means directly next to, right? We've talked about that word before. Good. We also have other names for these. This opposite and adjacent just came into play. This side can also be called the opposite. And this side, the one that's adjacent to the angle in question, is just called the adjacent side. We're going to move across to a second definition, which is what we're going to be talking about specifically today. We're going to be talking about the tangent of an angle. The tangent of an angle. The tangent is the ratio of the opposite the ratio of the opposite side to the adjacent side with respect to an angle. And we'll explain what that means. It's the ratio of the opposite side to the adjacent side with respect to an angle. So again, I'm going to draw a right angle triangle. Right angle triangle. And we're going to take this angle right here, this slope angle, but instead of calling it the slope angle, we're going to give it a symbol. It's a circle with a line through it, and that symbol is called theta. Theta, it's a Greek letter. Theta. It's what we use to represent angles when we don't know the measurement of the angle. So we're going to call him theta. And then here we have the opposite side and the adjacent side. And according to our definition, the tangent of the angle theta, so that's right here, the tangent of angle theta is equal to the ratio of the opposite side to the adjacent side. It's equal to the ratio of opposite over adjacent. And this will be true in any right angle triangle. Okay? The tangent of theta is the ratio of the opposite side over the adjacent side. That probably sounds super confusing at this point, but we're going to take some more notes and we're going to do a few examples, and hopefully that will clear things up for us. We're going to take some more notes on what a tangent ratio is. We know it's the ratio of side lengths, right? It's the ratio of side lengths. Now, when we were in similar triangles, I'm going to draw two similar triangles here. Once I find some space. Let's draw two similar triangles. We've got triangle A, B, C, and that's a right triangle.
Is this for example 1?
Nope, this is still just continuation of notes there. And we've got a similar triangle here. Not similar like it's kind of the same, similar like it has three equal angles, three pairs of equal angles. We're going to call that one D, E, F. So there's our two similar triangles. Yours don't have to be that different. Mine second triangle is huge. Definitely doesn't need to be.
So I can make this in case.
You should be able to tell that one is bigger than the other one so that they're not the exact same triangle. Yeah, that would help you understand the notes. So we know that in similar triangles, the ratio of corresponding sides are equal. So let's consider angle C here. What's its corresponding angle in the bigger triangle? Angle F corresponds to angle C, which means that the side length AC corresponds to DF, FE corresponds to CB, and AB corresponds to DE. So we have all those pairs with regard to similar triangles, right? Okay. The tangent of an acute angle, so if we take angle C, what is the tangent ratio here? What sides would we be looking at? We'd be looking at opposite over adjacent, right? Opposite over adjacent. And the same thing in F, we'd be looking at opposite over adjacent. Does that make sense? Now, because AB corresponds to DE, and they have the same ratio as BC has with EF, okay, then we know that this angle and the ratio, the tangent ratio of this angle is constant no matter how big this triangle grows. We'll understand that a bit in a second. So if we take the tangent of C, which equals in here the rise over run, which equals AB over BC, and in our big triangle, we take the tangent of F, which is opposite over adjacent, DE over EF. That's what we're talking about here. By similar triangles. There's only a little bit more to go, so hopefully you have the space for it. What does similar triangles tell us? Yeah, so in similar triangles, we knew that the ratio between AB and DE, so the ratio between AB and DE is equal to the ratio of BC and EF, because the ratio of corresponding sides will be the same, right? Well, now look what happens. Mathematically, we can divide both sides by BC and then multiply both sides by DE. And look what happens. We're going to do that in a couple of steps. So I'm going to divide both sides by BC. I'm going to take this and divide it by BC. And I'm going to take this side and also divide it by BC. And then here we're going to multiply both sides by DE. Multiply both sides by DE. I'm showing all these steps, but really it might be easier to just do a different way. But now we're going to multiply both sides by DE. and then I'm going to just explain to you how the math works here. So let's look on the right side here. If we've got BC in the top and we're dividing it by BC, those guys are going to cancel out. Okay? Then we've still got EF in the bottom, and we're multiplying 1 over EF times DE. Well, does that DE go on the top or the bottom? It goes on the top because it's top times top. So on the right here, you're left with DE over EF. Same thing over here. We're going to divide by BC, so that's going to put BC in the denominator, and we're going to multiply by DE. Well, what's that going to do? That's going to cancel out the other DE. So we're going to be left with AB over BC. So now we've shown using similar triangles that AB over BC is equal to DE over EF. Look what we got as our tangent ratio of C in our little triangle, AB over BC. And look what we got as our tangent ratio of F in our big triangle, DE over EF. And look, they're equal. Okay? So the tangent ratio of the corresponding angles, the ratio is going to be the same no matter how big or small your triangle gets. So basically, if we think about that again, I could stretch this line segment as far as I want and stretch this line segment as far as I want and still make a right triangle. Then the tangent ratio of F will always be the same, no matter how big or small the triangle is. Make sense? Alright, using what we know about tangent ratio, we're going to dive into our examples. And we are asked in example 1 to find the tangent of theta for each triangle, expressed as a fraction and as a decimal, correct to 4 decimal places. Now, why are we expressing the ratio as a decimal to 4 decimal places? Why are we keeping so much information?
Keep it as accurate. Yeah.
Keep it as accurate as possible. Okay? So here we go. In A, we have a triangle. I'm going to draw the first one, but I'm not going to draw the rest of them because you have the pictures right in front of you, right? Yep. So we've got a 12, 13, 5 right angle triangle. And we're looking at theta over here. And we need to find the tangent of theta. Well, tangent ratio deals with what sides? Opposite over adjacent. So the tangent of theta is equal to op over adjacent. What's the length of the opposite side? 5. What's the length of the adjacent side? Yeah, but it can't be the hypotenuse. So in tomorrow's lesson, you're going to learn that there's a third side, opposite, adjacent, and hypotenuse. So adjacent means it's not the hypotenuse, it's 12, right? It's the other leg.
So it's the flat one.
Okay, so we've expressed the tangent of theta as a fraction. Good. Now what? As a decimal. Throw it in your calculator. Give it an approximate sign.
Yeah, 166.
So rounded to 4 decimal places is 0.4167. Good job. Alright, heading on to B. I'm going to do B with you. I'm going to allow you to do C on your own. So B, I'm not going to draw. But again, each time we know that the tangent of theta is equal to the ratio of the opposite side over the adjacent side. And we're in a different triangle, so we just need to make sure that we identify properly opposite and adjacent. So in this situation, which of the legs is opposite? Careful, is that opposite theta?
Oh,
6.8. So it doesn't matter which one is longer or shorter, it matters where it is in the triangle. And the adjacent side length? 4.5, right, not the hypotenuse. So there we have it expressed as a fraction. Let's go ahead and express it as a decimal in our calculator.
1.511.
And we make sure we round to 4 decimal places.
No, it's repeating.
1.5111. Done.
You put a thing on it? Yeah.
Nope, because it's rounded to 4 decimal places. Just like we didn't keep going 6, 6, 6, 6, 6, 6, 6 with a hat on it. It's rounded to 4 decimal places. That means you're either rounding up or down. So you're looking at the 5th decimal place to decide if this one should go up or down. So same thing here. The next one is 1. That means this one stays down at 1, and that one goes to 0. That's rounded. Okay? We've lost some information, but that's okay. We were called to round it to 4 decimal places. Go ahead and try C on your own. Make sure you identify adjacent and opposite sides correctly. Go ahead and double check your answer for C on the board. As a fraction, it should say 4.5 over 6.8, and as a decimal, you should say it is approximately 0.6618. Example 2 is quick and painless. We're asked to evaluate each of the following with a calculator, and then record your answers, rounded again to 4 decimal places. So we've already learned that tan of theta can be expressed as a ratio, as a fraction, but it can also be expressed as a decimal. Okay? When you put it in your calculator, it's going to give you the decimal answer. So it's still a ratio, but it's expressed as a decimal, and we need to record it rounded to 4 decimal places. So for A says to find the tangent of 25 degrees. You literally just go in your calculator, you find your tangent button, you press it, you hit 25, and you hit enter. If you have an older calculator, sometimes you need to hit 25 first and then hit the tangent button. But either way, your calculator will give you this answer, 0.4663, rounded to 4 decimal places. Go ahead and do B, tangent of 60. And remember, these are approximate answers. Try that in your calculator. The tangent of 60 degrees should come out with 1.7321. Okay, so far we've done it pretty simple math. To find the tangent of 25, you just plug it in your calculator and it will give you a ratio. But what if you're given the ratio, but you're not given the measure of the angle theta? Well, it turns out we can undo the operation of tangent by using the inverse of tangent in the same way that we can undo addition by subtracting, or we can undo division by multiplying. So we're going to take a couple notes on what an inverse operation is. So inverse operation. Yep, this is your notes under that little note section. An inverse operation. This is an operation that undoes another operation. I don't think I spelled operation right. Undoes. I might be making up new words.
Undoes.
Okay, so let's make a little chart here. Just a small chart. On the left, we're going to have an operation. And on the right, we're going to identify the inverse operation. So on the left, if I write an addition symbol, what's the inverse operation? Subtraction. If I write a subtraction symbol, the inverse operation is addition, because it undoes the original operation. Alright. What about multiplication? What about division? Oh man, you guys are good. What about tan?
Long. Negative tan.
Hey.
Long.
It says we need to take the tan of
Square.
No.
an angle. So how would we undo that?
Press this tan -1 button.
Yeah, press the tan -1 button on your calculator. It's called tan inverse. Okay, it's the inverse tan function. It will undo a tan operation.
Hey.
So for instance, if you took
Shift tan. You shift tan. I don't have the word shift.
Shift table.
Or second function tan
Oh,
on
yeah,
your calculator. Yep,
yeah,
second function
yeah.
tan. All right, let's see how well this works. Let's look at example 2a that we already did. So example 2a. In example 2a, we found out that the tan of 25 degrees equaled 0.4663. If that's true, then it should also be true that the inverse tan of 0.4663 is approximately 25. Go ahead and punch second function tan, 0.4663 in your calculator, hit enter, and see what you get.
24.999639959.
Whoa.
Sound good?
Yep.
Nope. You nailed it. Essentially, all we did there was undo the tangent operation. In example 3, we are asked to find an angle using the tangent ratio. So this time, instead of finding the ratio and the side lengths, we're going to be actually finding an angle. So we're going to be using our inverse tangent operation. Fiona is building a skateboard ramp. She wants the ramp to rise 1 meter. Oh, and I'm going to draw a diagram right away. She wants the ramp to rise 1 meter over a horizontal distance of 2 meters. At what acute angles should she cut the wood, rounded to the nearest degree? So Fiona is looking for both of the acute angles in her diagram. She wants to find the measure of angle A, and she wants to find the measure of angle B. And do we already know the measure of angle C?
Right angle.
It's a right angle. It's 90 degrees. So step 1, always sketch and label a diagram of the ramp. We can also identify that when we're talking about angle A, so let's find angle A first. I'm going to find the measure of angle A by using the tangent ratio. So the tangent of A is opposite over adjacent. So if we're looking at A, what's opposite of A? What's side length? We're looking at a ratio of side lengths. So 2 and adjacent is 1. So we've got the tangent of A is equal to 2 over 1, right? But we want to find out what the measure of angle A is. So right now, the tangent operation is being done to A. So how are we going to get that tan away from A?
Just wondering, wouldn't it be opposite because you have your tangent would be at B and your right angle is at C?
Right now we're looking for angle A. So whenever you're talking about the angle, you choose, you're doing the opposite of angle A and adjacent of angle A. When we go to angle B, then 1 will be opposite and 2 will be adjacent. So it'll change. Okay? Angle C, we already know it's 90 degrees. Okay? Good. So we have the tangent of A is equal to 2, right? 2 over 1 is just 2. Let's write that step. How am I going to get the angle A by itself?
Divided by.
I need to take the inverse tan of both sides, not divided by. It's not attached by multiplication, so division won't undo it. It's attached by tangent. It's the tangent operation. So I'm going to take the inverse tan of both sides. So now I'm going to get that the measure of angle A, because I take the inverse tan of this, really just undoes tangent. And I take the inverse tan of this side, and I get that the measure of angle A is approximately, anyone have that in their calculator? 63.43 degrees.
Why is it a lower than the number of
Okay, so we have found the measure of angle A. So if I draw my triangle for Fiona again, we've got A, B, C, where C was a right angle. She's got a rise of 1 meter and a run of 2 meters. We found angle A, 63 degrees, approximately. Now, there are two methods for finding angle B. Can anyone think of what the two methods would be? Could we do the same thing again that we did to angle A? Yeah, we could use the tangent ratio. So method 1, use tangent ratio. And we'll do that one first. So this is for finding angle B. Yep, find, I'll write that on top, find angle B. So we can use the tangent ratio again. The tangent of B is opposite over adjacent, which now in this case is 1 over 2. And then to find angle B by itself, we take the inverse tan of both sides. So it's equal to the inverse tan of 0.5, or 1/2, same thing. If you put that in your calculator, you'll get that angle B is 26.56, or approximately 27 degrees. That's for finding the measure of angle B.
Oh, that looks a little.
Or number B.
It's all just the same example. Example 3 is not split up into ABC.
It is.
Yours is?
Yeah.
No, it's not.
Oh, it's just
It is.
No, it's not.
A and B.
Yeah, that's okay. Yep, yours is split up, so this is part B.
Oh, from a nice.
Can anyone think of the second method for solving for angle B? Lindsay. Yeah, we already know that the sum of interior angles in a triangle is 180. We know this one, C is 90, A is 63. So really, we know that A and B are complementary angles. They need to add up to 90. But anyway, we'll say this method is called geometric. Yeah, thanks. Geometric reasoning. Because we know that the measure of A plus the measure of angle B plus the measure of angle C is going to equal 180 degrees. That's the sum of the interior angles of a triangle, any triangle. We know that the angle C is 90. We know that the angle A was 57. Nope, 63. And so to find the angle B, we just need to subtract those from both sides. 180 minus 90 is 90. 90 minus 63 is 27 degrees. And always remember your little circle when you're working with degrees. So method 1 will always give a more accurate answer. Going right back to the triangle and using the sine ratio will always give you a more accurate answer. Okay? But in order to solve a triangle, you can always just use example 2 as well if you don't need an exact answer. In example 3, we found the measure of an angle using a tangent ratio. In example 4, we're finding a side length using the tangent ratio. So example 4 says, find the length of x in the diagram rounded to the nearest tenth of a centimeter. And you can see the information that we're given there. We're given one of the side lengths, and we're also given the measurement of an angle there. So let's use tangent. We're going to write a tangent ratio for the given angle in terms of the side length. So we know that the tangent of any angle, in this case we're given the angle is 28, is going to be equal to the ratio opposite over adjacent. Do we have any of that information with regard to the given angle? Do we have opposite? Well, opposite is x, and adjacent is 9.2. Well, now I'm using my algebra skills and my ratios. How am I going to solve for x?
Divide both sides by 9.2.
Careful, it's already being divided by 9.2.
Multiply.
I need to multiply both sides by 9.2. So watch what happens. If this side gets multiplied by 9.2, I'm left with 9.2 times the tan of 28. Okay, you may not multiply 9.2 times 28. That is incorrect. It's the tangent of 28. Okay? So there's no value of 28 here at all. It's the tangent of 28. And that's going to be equal to x. Now this you can just punch in your calculator. There's a couple different ways to do it. Okay? I would start, because multiplication is commutative, you can do this in whatever order you want. I would hit tan of 28, hit enter. And then times 9.2.
4.8.
If you've done it correctly, you should get 4.891 yada yada yada. And because it's a word problem, we'll finish it with a sentence. The length of side x is about 4.9, and what units was the triangle measured in? Centimeters. Way to go. All right, our final example for the lesson 5, solve a multi-step problem using the tangent ratio. It's so nice of them to tell you right off the bat it's going to be a multi-step problem. Otherwise, you'd have to think of it all by yourself. Okay, in the picture you have a radio transmitter. A radio transmitter is to be supported with a guy wire. A guy wire, you can see in your picture, it's just the wire that attaches to the ground and the pole and holds it up. Usually there are guy wires all around it, right? Pulling it in all different directions to support it. Have you ever seen that? Like a tall antenna tower has wires all across it? Yeah? Okay, good.
Didn't quite look like that, but.
Here we go. The wire is to form a 65-degree angle with the ground and reach 30 meters up the transmitter. So there's some good information for our diagram. The wire can be ordered in whole number lengths of meters, and our job is to determine how much wire should be ordered. So we're going to use our tangent ratio of the given angle, which is 65 degrees, to find the distance d from the tower that the guy wire should be secured. So we're going to find the length of the that we need here, but we're going to take 2 steps to do it. So I'm going to draw the same thing that you have, kind of, but we're going to draw a simplified diagram. You should do it as well. We've got the length of the wire, and we have the distance that the wire is going to connect with the ground and the pole. And the height here, this would keep going, but the height that the wire reaches the pole at is 30 meters. So there's all the information that we have so far, and we also have the angle that is made, 65 degrees. Now, this is a 2-step problem because so far, using tangent, I only have the ability to relate the opposite side with the adjacent side. And what I really need is the hypotenuse. But I don't have those skills yet to go directly from the angle to the hypotenuse. But if I get the opposite side and the adjacent side, what other property of a triangle can I use? What other formula? A squared plus b squared equals c squared, which is called the Pythagorean theorem. Okay, so that's going to be step 2. Well, let's go ahead and take on step 1. Step 1, we're going to find the length of d, because I know if I have d and this opposite side, I can use Pythagorean theorem. So the tangent of 65 is a ratio that relates the opposite to the adjacent side. So I've already got the opposite side is 30 meters, and the adjacent side is d. Now you'll notice in this one that the variable is in the bottom. Okay, that's a bit uglier to find out and to work with. So I'm going to do it in 2 steps to show you how the algebra works. Another helpful way to do this is to think of a division triangle. Have you ever seen a division triangle before?
Distance b or something.
Yep, you use it in science a lot. But basically, whatever's on top goes in the top, and then whatever's here goes in the bottom. And all this does is illustrate the relationship between these numbers. 30 over the tangent of 65 is equal to d. 30 over d is equal to the tangent of 65. And the tangent of 65 times d is equal to 30. So all of those relationships exist, and this triangle helps us to illustrate that. And it's true. Look what we've been given. The tangent of 65 is equal to 30 over d. That's exactly what we said. The tangent of 65 is equal to 30 over d. We're trying to find d. So our triangle tells us that using these values, d is equal to 30 over the tangent of 65. Okay? That's how to do it using a division triangle. I'm just going to quickly do it algebraically so that you can see the math behind it all. Tan of 65 is equal to 30 over d. I don't like how this is. I'm going to multiply both sides by d to get d out of the denominator. So if I multiply this side by d, I'm just left with 30. If I multiply this side by d, I'm left with d times the tangent of 65. Well, now I can get d by itself. I simply divide both sides by the tangent of 65. So I'm left with d equals 30 over the tan of 65. Again, exact same statement using either method. And we can throw that in our calculator. We get that the measure of d is we're not even going to calculate it yet because we don't want to lose any information. So we're just going to use this as d. Okay? Okay, ladies and gentlemen, in step 2, we are going to apply Pythagorean theorem. Pythagorean theorem we know is a squared plus b squared equals c squared. And of course, in our triangle, we don't have a, b, and c, but we do have a hypotenuse, which we know is always c. It's called w. And we have two legs, and it doesn't matter which order we do them in. So we've got 30 squared plus d squared. Now we have found the length of d. So we can fill that in. We've got 30 squared plus d squared, which is 30 over the tangent of 65. Remember to square it. And that equals w squared. Now I actually still don't need to make any calculations yet because I can take the square of both sides. Sorry, the square root of both sides. I'm going to swap sides here also. So the square root of w squared is just w. And then we got a big square root symbol here. And underneath it is going to be 30 squared plus, in brackets, 30 over the tangent of 65 squared. Now when you do it in your calculator, you can do it step by step, or very carefully with correct brackets, you can actually do the whole thing all at the same time. You know that 30 squared is 900. 30 times 30 is 900. And if you carefully type this into your calculator, you will get an approximation for the length of the wire as 33.101, and that's measured in meters. And now we look back to the original question to see if we actually answered what we needed to answer. It says, wire can be ordered in whole number lengths of meters. How much wire should be ordered? If we need this much.
34 meters.
Yeah, 33 meters won't be enough. So we need to order, we should order 34 meters, at least. Good job. Your homework is at the bottom of the page. 330, 1 through 12. Just lots of using the tangent, all different ways. And look through your examples, because we did 5 different examples, right? So most of the problems will match the examples that we did.